Gravitational field. Newton's law of gravitational attraction states that the force of attraction between two given particles or bodies is directly proportional to the product of their masses and inversely proportional to the square of their distance apart. For particles or bodies of masses m and capital M separated by a distance r, the force of attraction between them is force F is equal to gravitational constant times the product of the masses m and capital M divided by the distance between them squared. This is equation 1. That is F equals to G small m capital M divided by R squared. The gravitational constant is given 6.67 times 10 raised to power 11 Newton meter squared kilogram per kilogram squared. Gravitational field intensity or gravitational field strength E at any given point in the Earth's gravitational field is the force per unit mass experienced by an object at that point. In formula terms, gravitational field strength is given by F, that's the force experienced by the body at that point, divided by the mass of the body there, F over M. The unit of gravitational field strength is Newton per kilogram. The acceleration due to gravity on the Earth's surface is equal to the Earth's gravitational field strength. The gravitational field strength is given by Gm over R squared, where R is the radius of the Earth. Next is gravitational potential represented by letter V. The potential at a point due to the gravitational field of the Earth is equal to the work done in taking a unit mass from infinity to that point. Gravitational potential is given by this formula. V is equal to minus Gm over R sub E. G is the gravitational constant, M is the mass, and of course R sub E is the radius of the Earth. The gravitational potential at infinity is 0. Next is escape velocity of an object. This is the velocity with which an object, example a fired rocket, moves out of the influence of the Earth's gravitational field, maybe to infinity. Escape velocity V is equal to the square root of 2 times acceleration due to gravity times the radius of the Earth. Here the letters are explained, where G is acceleration due to gravity, R sub E is the radius of the Earth. Satellites are kept in their orbits by the gravitational attraction of the Earth. The speed of a satellite of mass m, which circles the Earth of mass capital M, is given by V is equal to square root of the product of the acceleration due to gravity and the radius of the Earth. The parking orbit of a satellite. A satellite is said to be in its parking orbit if its period in that orbit is equal to the period of rotation of the Earth on its axis. When in its parking orbit, the satellite stays over the same place on the Earth while the Earth rotates. Example 1. Two spheres of masses 5.0 kilogram and 10.0 kilogram are 0.3 meters apart. Calculate the force of attraction between them. Gravitational constant is equal to 6.67 times 10 raised to power minus 11 Newton meter square per kilogram square. The options are A. 4.00 times 10 raised to power 2 Newton, B. 3.57 times 10 raised to power minus 2 Newton, C. 3.71 times 10 raised to power minus 8 Newton, and option D. 3.50 times 10 raised to power minus 10 Newton. The solution to this example is as follows. Solution. Let's first take the data. The masses are M1 5 kilogram, M2 10 kilogram. Separation, that's the distance between the spheres, 0.3 meters. Gravitational constant 6.67 times 10 raised to power minus 11 Newton meter square per kilogram squared. Applying Newton's law of gravitational attraction equation, from Newton's law, the force of attraction between the two bodies or two spheres is equal to gravitational constant times the product of their masses divided by the square of the distance between them. So if we substitute the values, we have 6.67 times 10 raised to power minus 11 times 5 times 10 divided by 0.3 squared. Thus, the force of attraction between the two spheres is 3.71 times 10 raised to power minus 8 Newton. From this solution, option C is correct. Example 2. If the distance between two suspended masses, 10 kg each, is tripled, the gravitational force of attraction between them is reduced to dash 1/4, B 1/9, C 1/2, D 1/3. The solution to the second example is as follows. Solution. Applying Newton's law, the force between the two masses is equal to gm squared over the square of the distance between them. For the first force, F1 is equal to gm squared over r1 squared. Cross multiplying F1 r1 squared should give us gm squared. If we fix the values, F1 alone will give us 6.67 times 10 raised to power minus 11 times 10 squared all over the distance between them squared. This will give us F1 is equal to 6.67 times 10 raised to power minus 9 all over r1 squared. This is my equation 1. Also, If the distance between them is tripled, if the distance between them is tripled, the new distance R2 is given us 3R1. Therefore, the force F2 will give me gm squared all over R2 squared. This will give me gm squared all over 3R1 squared. F2 will now give me 6.6 times 6.67 times 10 raised to power minus 11 times 10 squared over 9R1 squared. This is equation 2. Comparing equation 2 and equation 1, comparing equations 1 and 2, equation F2 is equal to 1/9 of F1. Thus, option B is correct. Example 3. A body is projected from the Earth's surface with the intention of letting it escape from the Earth's gravitational field. What is the minimum escape velocity of the body? Given is the radius of the Earth r, which is 6.4 times 10 raised to power 3 kilometers, and acceleration due to gravity g, 10 meters per second square. The options are A, 14 kilometers per second, B, 13 kilometers per second, C, 12 kilometers per second, D, 11 kilometers per second. The solution to this example is as follows. Solution: we are given the radius of the Earth to be 6.4 times 10 raised to power 3 kilometers, which is the same thing as 6.4 times 10 raised to power 6 meters. Then acceleration due to gravity is 10 meters per second square. Escape velocity V is square root of 2 times g times r. We fix the values into the formula. We have 2 times 10 times 6.4 times 10 raised to power 6. The escape velocity is square root of 1.28 times 10 raised to power 8. This will give us 11.3 kilometers per second approximately. This gives an approximate velocity of 11 kilometers per second. Option D is correct.